Hello, chemistry friends. Nice to see you again this week. Welcome to our third week of AP Chemistry Review, where we will be spending the second week on the big idea of structure and properties. Just to give you a sense of where we were last time. Last time we talked about scale, proportion, and quantity the first week, and then we did the first week of structure and properties. For those of you who were attending last week, apologies. I know there was an abrupt cut at the end. Thank you, thunderstorms. If you're in the area, you probably could guess why I had gotten cut off. The weather looks pretty clear today, so I suspect we will get through all of this. So all of this would include Structure and Properties Part 2. Be sure to stay tuned in the coming weeks for Transformations in Energy, which will take us right up to the AP exam in May. So our first big idea, how much stuff was in that stuff? Last week, how does structure influence properties? We spent a lot more time last week on structure than we did on properties. That's going to change this week. We're going to talk a lot more about properties with just a little review of where we were on the structure. As a reminder, last week we got through the top half of this stuff: electron configurations, periodic table trends, some covalent bonding, some Lewis structures, and we ended right on the tip of VSEPR theory and molecular shapes. So we're going to pick up there just for a little bit of continuity, and then we're going to dive into polarity and intermolecular forces and solids and liquids and gases and all of that good stuff, ending with some ideal gas law calculations. So VSEPR theory, if you recall, that stands for valence shell electron pair repulsion theory. It's nice to understand the structure of a molecule that we care about, like PCl3, but it's even more handy to understand the three-dimensional shape of that molecule. So how VSEPR theory works is we just kind of count the regions of electron density around the central atom. In this case, 1, 2, 3, 4 of them. Could be a lone pair, could be a bond. But remember, those areas of negativity really don't like being next to each other at all. Right, so what do? We want to space those as far apart from each other as possible, and nature has solved that problem perfectly, and the mathematical shape there is what's called the tetrahedron. So if we imagine that the areas of electrons kind of segregate themselves in that way, what we find here is something that is called trigonal pyramidal for the shape of PCl3, because it kind of looks like a pyramid with a triangular base, with the kind of lone pair of electrons right there at the top. On the other hand, this molecule only has 3 regions of electron density. So how does nature solve that problem? It simply spaces them straight up in the plane, right? 320-degree bond angles, and we get a perfectly kind of planar flat molecule that's just as you see it here in the page. That guy we happen to call trigonal planar. So there are lots of these VSEPR structures, which you can kind of conveniently put on one table. And really, there's a lot of information on this table, but it all really does make a great degree of sense, right? On one axis, we have the steric number, which is a fancy way of saying how many regions of negativity. And on the other axis, we have lone pairs. So how does this work? Let's fill in the table, right? If I have 2 regions of electron density and no lone pairs, well, they just spread out perfectly linearly. Right. If there are 3 regions of electron density, that we said was trigonal planar, but if one of them is a lone pair, it looks bent or angular, right? And the same game repeats in each row. So if you just kind of keep in mind the parent structure of each row, the next row, tetrahedral, we just think about what it would look like when I take away kind of legs from that tetrahedron, right? Each one being replaced with a lone pair. I take away one, it looks, oh, that's an error. It's actually trigonal pyramidal, as you guys know. Take away 2, bent or angular. I'll be sure to fix that. And then in the next row, trigonal bipyramidal, right? Here we have 3 in a plane and then an up and a down. Take off electrons, sawhorse, T-shaped, linear. And same thing here, octahedral, square pyramidal, square planar, T-shaped, and finally linear yet again. So lots of information there, but really it's not something you need to memorize so much as just understand how it works, which is always kind of preferable, I think. Other things you might want to know here are the bond angles, right? So those bond angles make sense. The only one that's probably a little weird to you is the tetrahedral bond angle of 109.5, so you might need to kind of memorize that one. And then the final column here is what's called the orbital hybridization, right? So the AP has decided not to go into all of the cool nuts and bolts behind orbital hybridization as much as I would like to, because it is kind of cool. But really how this works essentially is, if you think about, I don't know, let's think about that trigonal planar molecule, right? That's 3 perfectly spaced bonds. Well, how does that happen? Because the electrons that are being shared there, well, one of those electrons is in an s orbital and 2 are in p orbitals. Well, how does that work? Well, those orbitals, as it turns out, hybridize, and those 3 orbitals give rise to 3 sp2 orbitals, which are totally equivalent. So really, all we have to do is rely on that steric number, right? How many guys are hanging off the central atom, and just count orbitals up to there, right? S, sp2, sp3, sp3d. You just keep adding the next orbital until you get to the number of guys hanging off the central atom. So really, that's all you need to know about orbital hybridization. If you care about the details, look me up and we'll talk about it. So that's VSEPR. I wanted to close our discussion of bonding with kind of a little deeper idea, which does sometimes come up on the test, and that is, like, why do chemical bonds actually form, right? So let's consider 2 atoms that are moving toward each other, spaced far apart initially, and they're getting closer. So if we look at the energy versus the distance between those nuclei, right? We probably remember from basic physics and science classes that you have that everything's trying to lower its energy, right? I can pick up a pen and I drop it, and why does it fall? Well, because it's trying to lower its potential energy. In the same way, these bonds form because by forming, they can get to a lower energy. So as it turns out, the shape of that kind of potential energy curve kind of looks like this, right? If the molecules or atoms, pardon me, are spread far apart, there's really no interaction between them. So that energy is basically 0. We call the infinite separation kind of the 0 point of energy. As I bring them closer, however, now if they're atoms that want to form a bond, that want to share electrons in some way, they're going to get a little happier, right? They're going to be closer. That energy is going to be more positive. At some point, if you bring them the perfect distance apart, they're going to form a bond, right? And that's what we call the bond length, right? That distance, right? And the energy that they save by doing that, we call the bond energy, right? If we were to continue moving these a little closer, we'd find that actually their electron clouds start to overlap a little bit, which is why that energy curve in red shoots up really, really fast, right? Because those 2 atoms are just not going to get any closer together because of that strong repulsion from the electric clouds. So you want to definitely be able to understand a graph like this should you see it, and other things that might come up is how this relates to what we call bond order, right? As we saw in some of our Lewis diagrams last week, we saw single bonds, we saw double bonds, we saw triple bonds, right? What you need to know is that as I go from single to double to triple bonds, that bond energy gets greater. That is, this curve gets a little deeper, right? Also, the bonds get a little shorter, right? So just keep that in mind if you need to answer questions based on a graph that might look like this. Okay. So let's move on to totally new stuff that we didn't cover last week. So one of the real reasons we need to understand molecular shapes is to understand if those molecules are polar or not. So if you recall, we talked about bonds being potentially ionic or potentially covalent, right? And it really depends on the difference in electronegativities. There's a very large difference in electronegativities. One atom's going to buy electrons, the other one's going to sell them. You'll make 2 ions, and it'll be an ionic bond, right? If, on the other hand, I have like a diatomic molecule like oxygen, O2, right? Each of those oxygens is pulling equally hard, right? And they're going to share the electrons. That will be a nonpolar bond, but there are plenty of middle ground. So if we want to think about how that works, let's look at Cl2, chlorine gas, versus HCl. So Cl2, the Lewis structure, simply looks like that. But if we imagine kind of what this looks like, right? I have 2 chlorine atoms, and I'm kind of coloring them in here to show where the electrons are, right? The electrons here end up mostly between the atoms. Why? Because that's where the bond is formed, right? That's where the electrons are being shared. But you'll notice that it's completely symmetric, right? One chlorine isn't winning the tug of war here. It's a tie ball game. On the other hand, for HCl, it looks very different, right? For HCl, the electrons are unequally shared. Those electrons spend more time closer to chlorine than they do to hydrogen. So this is what we call a polar bond, right? Unequally shared. So there are two different types of notation you might see when looking at a polar bond. The first is this funky arrow with a plus sign on one side of it. It looks kind of like that, right? The plus side of the arrow is the positive side, and the straight side of the arrow, which looks kind of like a minus sign, right, is the negative side. You might also see notation that looks like this, delta plus and delta minus. What we mean by that, delta actually comes a little bit from calculus. It just means a little small piece, right? So we're saying it's not like a totally +1 charge or a -1 charge. It's just a little bit positive and a little bit negative, right? So either of those notations is fine if you have to denote something as polar. So, all right, so we know now that bonds can be polar, but what about molecules themselves, right? It takes actually more than polar bonds to make a polar molecule. For example, let's consider BCl3 and PCl3. At first glance, look pretty similar, right? Chlorine, super electronegative, way more electronegative than boron, way more electronegative than phosphorus. So we would expect maybe either both of them are polar or neither of them are polar. But as it turns out, spoiler alert, BCl3 is nonpolar, but PCl3 is polar. Why? Well, let's look at the Lewis structure and, more importantly, the molecular shape. Right, there's BCl3, and we know that it's trigonal planar, so it's completely flat, right? And I've kind of dropped the electrons from this last part of the diagram, forgive me. So if we think about those bonds, they are in fact polar, just like in PCl3. Right, but PCl3 is trigonal pyramidal rather than trigonal planar, but those bonds are still all polar, right? In each case, chlorine is winning the tug of war in both cases. But in the case of BCl3, if you literally imagine like a three-way tug of war, like in a plane, right? If everybody's pulling equally hard, the knot's not going anywhere, right? Those polar bonds, right, all have their own little what are called dipole moments, but they all cancel each other out, right? So the net dipole moment of that molecule is 0. It's a non-polar molecule. On the other hand, if you imagine kind of in like almost a vector way, right, adding these three arrows in PCl3, you'll find that, yeah, the kind of the horizontal components cancel, but if you add those three arrows all kind of pointing down, you end up with the vector pointing straight down, right? So this one actually does have a net dipole moment. So that means that PCl3 is going to be a polar molecule, whereas BCl3 is nonpolar. Right, and that's going to have really important differences in terms of how they behave. So it's important for you to be able to tell the difference quickly between polar and non-polar molecules. So let's do some drills, shall we? Water, everybody's favorite molecule. Yeah, clearly we all know that water is, or we should all know that water is polar, because that's a really important property. And why is that the case? Yeah, because if we look at the molecular shape, it's bent. So the oxygen's definitely winning the tug of war for electrons there, and I have a net dipole moment. CH4, on the other hand, tetrahedral, perfectly symmetrical, nonpolar. And in fact, even if CH4 weren't perfectly symmetrical, neither carbon nor hydrogen is electronegative enough to generate a polar covalent bond. So I don't care what the molecule looks like. If it's made of all carbons and hydrogens, it's nonpolar. Right, CO2, this one could be polar, right? Because oxygen's super electronegative, right? One of the three most electronegative atoms on the periodic table. But if you do the Lewis structure, you'll find that this guy's perfectly linear with two double bonds there. So that symmetry overrides the fact that those are polar bonds, but they ultimately produce a non-polar molecule. Xenon tetrafluoride, fancy molecule. This one ends up being square planar. So again, we have symmetry concerns that even though fluorine is super electronegative, we're not getting a polar molecule there. The cyanide ion, Cn minus, yeah, that guy's going to be polar because nitrogen is way more electronegative than carbon. That's a one-sided battle, so that will result in a polar molecule. Right. And finally, CH2O, as you might imagine, just one oxygen there pointing off in that direction. So that's going to be an unbalanced dipole moment. So this will result also in a polar molecule, right? So really important to know what's polar or not. Why? Because that's going to dictate how these molecules interact with each other. That is, it's going to have to do with the intermolecular forces between them. So what are intermolecular forces? Just like if you were to, go to the international gate at Dulles, right? You're traveling between nations, right? So intermolecular forces are forces between molecules, from one molecule to its neighbor. The ones that we're going to talk about are all going to be attractive intermolecular forces. Sure, if you jam two molecules close enough together, they're going to repel, but all of the long-range intermolecular forces that really we care about most are attractive intermolecular forces, right? And these are responsible for holding the molecules together and giving the substance, whatever it is, its shape, its size, what have you. Right, so a bunch of intermolecular forces that you're going to be responsible for knowing about, and let's list them here from weakest to strongest. Right, the weakest are what are called London dispersion forces. From there, we're going to go to dipole-induced dipole, and dipole we now know is just a polar molecule. And then dipole-dipole forces between two polar molecules. And that one has a special case, which I'm sure you've heard about, hydrogen bonding, right, which is nothing more than a special case of dipole-dipole forces, as we'll see. And then finally, the strongest would be ion dipoles. I know that's a lot, but we're going to go through them all in detail in just a moment. But the thing that we want to remember here, right, is that we care about these things because they give rise to properties, right? Knowing something about the intermolecular forces tells us something about the physical properties of the substance, right? From this, we can make arguments about, oh, which of these two guys should have a higher boiling point or a higher melting point or a higher vapor pressure, things that we can, again, touch, taste, and feel in the lab. So we're really working on these connections between the microscopic atoms and molecules and the macroscopic that we can actually measure. Right. So let's dive in a little more deeply and try to understand just how these intermolecular forces work. And I want to spend the most time actually on the first one, right? London dispersion forces. So these are forces that actually exist between two totally neutral molecules. Let's imagine a pair of neutral neon atoms, right? Why in the world would these two neutral guys want to attract each other? Well, let's imagine that one of these neon atoms starts to move closer to the other, right? So now they're next to each other. And now let's imagine that just for a split second, the electrons in that second atom happen to look like this, right? I mean, these electrons are always moving around. So at some instant in time, it could be the case that more of the electrons are on the left side than the right side. Well, what's that going to do? That's going to result in a temporary and small, but finite dipole moment, right? That overall net neutral neon atom, just for a split second, is kind of negative and kind of positive. Well, what's that going to do to its neighbor? Well, neighbor neon atom there now sees a negative charge. So what's going to happen to the electrons? Well, they're likely going to be repelled, right? They're going to run away over to the other side of the atom. And now we have two dipoles. So now these guys are going to attract each other, right? And that's what actually results in this attractive force between neutral atoms. But a split second later, and less than a second actually, more like a femtosecond, boop, gone. Right, the electrons have moved again, and now they're neutral, and now they're not attracting each other. But really, if you imagine, right, we talked about in our first week Avogadro's number being just a stupid big number, right? So even if this only happens very rarely between atoms and only for a very short amount of time, there are just so many atoms to talk about in any kind of measurable quantity of neon that there's going to be enough of these temporary attractive forces that it's going to provide some measure of attraction to keep this neon together, right? And this is why actually nonpolar things actually can liquefy and freeze, right? We'll talk a little bit more about solids, liquids, and gases, but you know, in order to become a liquid or become a solid, right, it's the intermolecular forces that are holding things together. We've got to get something, you know, like one of these molecules insanely cold to do it, but it can happen because these attractive forces actually do exist, right? So the other sets of Oh, right, pardon me. The other thing I wanted to talk about with London dispersion forces is their strength, right? So these London dispersion forces can be stronger, can be weaker. So two important factors there. The first is increasing what's called polarizability, and that's a fancy word. And the second one is increasing surface area, right? So let's look at these separately. First, increasing polarizability. Well, in order to have this attractive force, right, that electron cloud needs to, just for a split second, be polarized, be positive over here and negative over there. And the larger the electron cloud is, the larger the difference between the positive and negative side can be. Right, so if I consider two noble gases, argon and neon, right, argon has a heck of a lot more electrons than neon does. So that means that argon can sustain a larger temporary dipole. So argon ends up being more polarizable. So the intermolecular forces, the London dispersion forces between argon molecules, or argon atoms, pardon me, is larger than the strength between neon atoms. Great. Increasing surface area. Really, so in order for this to happen, right, these two molecules or atoms need to be close to each other, right? Because in order for one to kind of induce a dipole in the other, they need to be pretty nearby. So here, let's consider two molecules that are exactly the same size, if you will. Let's consider two isomers of C8H18. So again, these are some kind of fancy Lewis structures. Don't panic. You're not going to be responsible for drawing many of these. The first one actually is a compound I suspect many of you are familiar with, even if you can't name it right now. C8 might give it away. 888 octane, right? This is the stuff you put in your car to get around. The next one has a fancier name that I'm not going to go into, but basically it's just a different arrangement, right, of those 8 carbons and 18 hydrogens. So one is more close packed, right? The octane is kind of long and skinny, right? So they have the same volume because same number of atoms. But if you don't remember this fact from geometry, the closer something is to a sphere, right, the larger the volume to surface area is, right? A sphere has the least surface area for the most volume. So anything that gets closer to being a sphere is going to have less surface area. Anything that gets long and skinny is going to have more surface area per volume. So actually, C8H18 as octane, the top guy there, is actually going to have stronger London dispersion forces, and the smaller or the more compact one, more spherical one, if you will, at the bottom is actually going to have weaker London dispersion forces. Right, so you might need to know that two compounds both have LDFs, but be able to evaluate which ones are stronger. So moving on to the other types of intermolecular forces, which I think are kind of easier to kind of think about because they just seem to make more sense. Dipole-induced dipole. So the London dispersion forces are actually called induced dipole because that's kind of what's happening. Neither of those neon atoms, let's say, has a permanent dipole moment, but one happens and that induces the other. In the case of, let's say, HCl and Cl2 in solution, right, one of those, HCl, is polar, it is a dipole, but the other one is nonpolar. So if we imagine what that cartoon looks like, it might look something like this. So yeah, there are attractions between these guys. In fact, there will be attractions between the HCl and the Cl2 molecules. I can draw them in like this. So it's important to note that these aren't bonds. I'm just kind of drawing some dotted lines to show the interactions between one HCl that's going to be either positive or negative, which will induce a charge in that nonpolar Cl2. Are these strong forces? Not really. They're much stronger, let's say, if we had dipole-dipole interactions. That is, if we just had pure HCl. So if you look at the structure of HCl, even though it's a liquid and the molecules are clearly moving around, they do have some structure to them. In fact, they arrange themselves in these chains of dipole-dipole interactions. So here, if I draw them in, you can see that the positive hydrogen of one molecule tends to align itself closer to the negative chlorine or partially negative chlorine, right, of its neighbor, right? So we get these long kind of chains of interactions that serve to hold these guys together. Right. Hydrogen bonding, we said, was a very specific type of dipole-dipole interaction. In this case, we're going to look at it in, of course, water. But important to note that what is hydrogen bonding? It's simply the dipole-dipole interaction that exists between a hydrogen bonded to a nitrogen, oxygen, or fluorine, and the nitrogen, oxygen, or fluorine on the neighboring molecule. Why nitrogen, oxygen, or fluorine? Well, if you remember our periodic trends from last week, you recall that nitrogen, oxygen, and fluorine are the three most electronegative elements on the periodic table. So really the difference between dipole-dipole and hydrogen bonding, it's just a difference of scale, right? It's the same thing, but nitrogen, oxygen, and fluorine are capable of creating much stronger intermolecular forces. So we just group them into their own category, give them their own name, and call it hydrogen bonding. Here we can see that, again, those positive hydrogens align themselves in a way that puts them next to the negative oxygens of their neighbors, right? And water actually has a lot of hydrogen bonding because it has two hydrogens, right? So you'll see that compared to my HCl cartoon, right, those water molecules are even more interconnected, right? A water molecule can have up to 4 hydrogen bonds between its neighbors. So that's one of the reasons that water, for what it is, has a really high boiling and melting point, but we're going to talk about that in just a second. And finally, the last strongest type of intermolecular forces is ion dipole. Because remember, yes, even though hydrogen bonding is pretty strong, those oxygens don't necessarily have a negative charge, they have a partially negative charge, right? And those hydrogens have a partially positive charge. Well, what if we involved some guys that actually have whole charges? Right? Let's dissolve some salt in water, right? What's going to happen? Na and Cl are going to break apart, right? The reason that they break apart is because they're solvated or made happy or surrounded by water molecules in a very particular way, right? According to my color scheme here, chlorine is the purple guy and sodium is the green guy. And you can see that that negative chlorine is surrounded by the positive hydrogens of water, kind of this like water cage around it that can make those really beneficial, attractive forces. And similarly, oxygen kind of turns its back on sodium, right? And presents the negative, or water turns its back on sodium, pardon me, and presents this negative oxygen towards the sodium. So that can solvate it. Right, so those are the different types of dipole forces. So again, we went from is it polar or not to what kind of intermolecular forces, because intermolecular forces determine properties, right? So the stronger the intermolecular forces are, the lower the vapor pressure is. The lower the vapor pressure is, the higher the boiling point is, and melting point for that matter. So vapor pressure, I know, is a word that gets thrown around a lot, but not one that most students are super comfortable with. So let's talk just for a hot second about what vapor pressure actually is, right? So let's imagine I have 2 flasks here filled with 2 different liquids, one of which has weak intermolecular forces and the other strong. So what I've got here is a liquid, and then let's call it air above the flask above it. But there's going to be more than air, right? Because even if I'm below the boiling point, some of the molecules in the liquid are going to escape into the gas form, right? It's evaporation. You know this happens, right? Other molecules that are in the gaseous form are going to recondense. So that's going to establish an equilibrium, which we're definitely going to be hitting next week hard, an equilibrium in the flask. So there will be some equilibrium number of gas molecules, of liquid molecules that have escaped the liquid phase into the gas phase, right? So what does that have to do with intermolecular forces? Well, the intermolecular forces, be they hydrogen bonds or London dispersion forces or what have you, right? Those are the forces that are holding those molecules in together as a liquid. So you have to overcome those intermolecular forces in order to vaporize, right? So that's why the stronger the intermolecular forces are, the lower the vapor pressure is, right? If I considered now my flask on the other side that has a substance with much stronger intermolecular forces, well, it's not going to have nearly as much vapor or liquid escaped into the vapor phase. Why? Because it's all held tightly together as a liquid, right? So if there are fewer molecules that have evaporated to the vapor phase, they're going to exert less pressure on the walls of the flask. We'll talk more about pressure today. And that's really what we call the vapor pressure, right? The vapor pressure is nothing more than the pressure of the formerly liquid molecules that have escaped into the gas phase. Right. Well, what does that have to do with boiling point? Well, a good definition of boiling point, right? It's the temperature at which the vapor pressure equals the atmospheric pressure, right? And you know this if you've ever boiled some water, right? The water begins to kind of steam a little bit long before it hits like a rolling boil, right? As I get hotter and hotter, right, these molecules are getting more energy and are more likely to be able to escape those intermolecular forces, right? When the vapor pressure equals the atmospheric pressure, well then all of the liquid is going to want to escape into gas, and that's what we call boiling. All right, so now that we understand that the links on that chain between intermolecular forces and some properties, let's again do a little practice. So let's look at a few questions here. Which of the following has a higher boiling point? Well, water, H2O, or hydrogen sulfide, H2S. Well, those are pretty similar. Oxygen and sulfur are even in the same family, right? H2O, H2S. But if you think about what are the intermolecular forces, right? Water, as we know, hydrogen bonds. But sulfur is not nitrogen, oxygen, or fluoride, right? Or fluorine, right? Sulfur doesn't hydrogen bond. It can only have dipole-dipole forces. H2S bent, just like water is, but still those dipole-dipole interactions are weaker than the hydrogen bonding. So stronger intermolecular forces, higher boiling point, right? Chlorine versus bromine. Let's take a look at that one. Both of those guys are totally symmetrical and nonpolar, so they both have London dispersion forces. But as we talked about, the London dispersion forces get harder or get stronger as the molecule gets larger. So which molecule here is larger? Bromine is. So those bromines are more polarizable because they have more electrons, leading to greater intermolecular forces and a higher boiling point. And finally, hydrofluoric versus hydrochloric acid. And again, we're going to have another battle between hydrogen bonding and dipole-dipole interactions because fluorine's super electronegative, and we know that hydrogen bonding is stronger. Right. On the other hand, which has a higher vapor pressure. So now we're going to be looking for not the one with higher intermolecular forces, but with weaker intermolecular forces that will allow more of those molecules to vaporize and escape into the gas phase. So here, CO, carbon monoxide, is polar, dipole-dipole. CO2, just dispersion forces, because as we showed before, it's linear and nonpolar. So that means that a guy with lesser intermolecular forces will have a higher vapor pressure. Here, CH3Cl versus CH4. Obviously, the CH4, right? Just dispersion forces, symmetric, carbon hydrogen, nothing strong enough to pull a dipole. So that's going to be the winner. And finally, I threw something at you that wasn't like totally formula based. Salt water versus water. Right. Well, water we know will hydrogen bond, but salt water, kind of like we saw earlier, has ion dipole interactions, right? And those ion dipole interactions actually serve to keep the water molecules like held more tightly in the liquid phase. So water will have a higher vapor pressure, right? So that salt water actually ends up having a higher boiling point, right? So up until now, so great. So now we know how to figure out various boiling points and melting points and all sorts of stuff about these solids as they go from solids to liquids or liquids to gases. But really, all of the talk that we've done so far has kind of been about covalent bonding, right? It's been all about molecular solids, that is, things made of molecules. But other solids definitely exist. In fact, there are a couple that you're going to need to know about for the purposes on this test. The first, molecular solids, right? Like, I don't know, ice, we'll call it. Compare that to an ionic solid, which would be something like sodium chloride, right? Now, salt, sure, it comes out of your salt shaker in really, really small pieces, but those pieces certainly aren't molecules, right? In fact, salt doesn't exist in molecules, right? It's a crystalline solid, right? That is, the sodium and the chlorine are packed in this kind of alternating structure to minimize the repulsive forces between the like charged guys and to maximize the attractive forces between the oppositely charged guys, right? So no such thing as a molecule of salt, right? Another example, and by the way, just because I'm covalent doesn't mean I form molecules, right? There are things called covalent network solids. Diamond is the classic example. I've used silicon oxide or quartz here. has to be non-polar, non-metal atoms involved here. Metalloids actually tend to do this a lot, so thus silicon. Yeah, so we have these also in their extended network of kind of extended network of bonds, creating one kind of, I don't want to say large molecule, but one large crystal. And finally, metals, right? If I just have a piece of iron, a piece of copper, right? What's going on there? Actually, those are crystalline as well, but a really key difference here when it comes to metals, right? What occupies those lattice positions? It's actually just the cations. It's just the positive ions, in this case, a copper 1 or copper 2 ion. And as it turns out, they're floating in a sea of electrons, right? Unlike an ionic solid or where the electrons have been stolen by their neighbors, or unlike a covalent bond where the electrons are being shared between two molecules, in a metal, the electrons kind of don't belong to any of the atoms anymore. They're free to float and flit back and forth between all of these nuclei in their fixed kind of lattice positions. So that's going to give rise to very different properties. When I think about melting and boiling point, we said in order for something to melt or boil, right, we have to rip those atoms or molecules apart. Well, for molecular solids, what are we breaking or what are we overcoming? We're overcoming intermolecular forces. That's not that hard. It doesn't take that much energy, which is why molecular solids tend to have pretty low melting or boiling points. On the other hand, ionic solids, well, now it's ionic bonds that are holding those atoms together. That's much harder to break than just intermolecular force, resulting in much higher melting and boiling points. And the same is true for covalent solids, right? Now we don't have ionic bonds, but covalent bonds holding everything together, right? It's really hard to melt a diamond. Metals, kind of in the middle, right? They tend to have, obviously, boiling a metal is hard. We don't think about that happening. But metals typically have much lower melting and boiling points than do ionic or covalent network solids. So other things that are going to be influenced, conductivity, right? Both in terms of heat and electrical conductivity. Molecular solids, so let's think about electrical conductivity. What do we need, right? What does it mean to be a conductor? Well, it just means that electrons can flow through it pretty easily. Well, in our first example, molecular solids, we said those electrons were all kind of being shared and stuck on the molecules that they're forming. So that's going to be a poor conductor. Ionic solids, yeah, all of those positive and negative ions, sure, they're there, but they're locked into their rigid crystal structures, and those also are very poor conductors. That being said, we can make them good conductors in two ways, right? Salt, a big hunk of salt, is actually not going to conduct electricity, but I can do two things to it to make it conduct electricity. One, I can dissolve it in water. That would create salt water, right? And then we'd have ions in motion, right? Electrons can pass much more easily through that. Or if I did get it hot enough, and by hot enough, we'll talk a little bit more about this on the next slide, but 1,000 degrees or so. Yeah, if you were to melt the salt, well, then we'd have free flowing and free moving charge, and we'd have a good conductor. Right. Covalent network solids, yep, not going to be good conductors at all. And of course, metals are excellent conductors. Why? Because as we said, those electrons are just free to roam from one end of the piece of metal to the other, right? And then finally, in terms of their properties, right, molecular solids can be kind of crystalline when frozen, but are generally amorphous. Ionic solids, salt, right, if you actually kind of look at pieces of salt under the microscope, right, they're kind of sharp. Right, they fracture right along these planes because that's kind of how these crystals are put together, right? So they're not going to bend; they're typically going to shatter, right? That same thing is true about covalent network solids, which tend to be really rigid and hard. Metals, as we know, don't always shatter, but they can bend, right? Again, because it's not like every positive guy is locked into place by a negative guy or a covalent bond. Yeah, we have a crystal structure, but it is definitely capable of rearranging itself. So metals have these properties of being malleable and ductile, which are just fancy words meaning we can bend them around a lot. Great. Yeah, all of our talk up until now has been about molecular solids, but I did want to acknowledge the fact that there are other types of solids we care about. One more slide on ionic solids, because this is something that kind of comes up from time to time as well. So most of our talk about intermolecular forces has been how do we understand the different properties that different molecular solids have? Well, I can ask the same question here. How do we understand the different types of properties that different ionic solids have? Well, for molecular solids, we thought about the intermolecular forces because those are the forces holding the molecules together. Here, we're going to think about Coulomb's law because it's that electrostatic attraction that's holding, that is that ionic bond that's holding all of these guys together. So let's look at some data real quick. So here are three ionic solids, right? Potassium bromide, sodium fluoride, and magnesium oxide. And those are the melting points. And those are pretty darn high. I'll let you know those are Celsius, right? So really high in Fahrenheit that you would typically relate to, but either way, high, right? But there's a really big difference there. So why is it that sodium fluoride is melting at a higher temperature than potassium bromide? Well, let's take a look at them, right? We might remember from our periodic trends that this is kind of, my rough estimate. I figure not perfectly drawn to scale, but I'm trying. And that is, I'm definitely showing that both potassium and bromine are much larger than sodium and fluorine. Why? Well, they're down one row on the periodic table, which means they have an extra layer of electrons, and that's a larger atomic radius. So how does that affect the attractive forces? Well, that intermolecular, internuclear separation distance is just larger in KBr than it is in NAF. So if we think about Coulomb's law, right, the force is proportional to the charges divided by the separation, right? So potassium bromide has a larger separation between nuclei, meaning the overall electrostatic force between the two is going to be smaller, meaning it's a little easier to overcome. I don't need as much energy, and I can do it at a lower temperature. Right. What about the big winner here? What about magnesium oxide? Well, that has to do with the numerator rather than the denominator, right? Magnesium oxide, about the same size as sodium fluoride. It's pretty close. Magnesium's a little smaller and the oxygen's a little bigger. But overall, the internuclear separation distance is almost exactly equal. But the charges here are definitely not. Magnesium +2, oxygen -2. So if you just think about that part of it, well, times 2 times 2, that means that the electrostatic force will be almost 4 times as great. And what do we see? Yeah, we see a really big difference in the temperature required to melt magnesium oxide compared to sodium fluoride. Right. So we can also kind of play these games in terms of understanding properties for ionic solids as well as the molecular solids that we're more comfortable with. So let's turn our attention from solids to some other states, solids, liquids, and gases. You might recall from chemistry that you've taken that you spent a lot of time looking at like phase diagrams, right? Pressure versus temperature, solid, liquid, gas. Yeah, those aren't on the AP. They consider those kind of arrogantly prior knowledge that it's not tested on the AP. So if you didn't like those diagrams, don't worry, they're not here. But we still want to kind of be able to argue if we have to, because again, I think that this AP this year, it's going to be all about writing things down. It's going to be all about explaining in sentences. So I want you to be comfortable explaining in sentences why solids are solids and liquids are gases and gases. So what is the difference between these guys? Well, if I just throw up a couple sketches here, if I said which one of those two looks most similar, generally you'd say solids and liquids. Yeah, they're both what we call condensed phases, right? Their densities are similar, right? I mean, not the exact same, but pretty close. Right, same order of magnitude. On the other hand, gases, way different, right? In a solid and liquid, the atoms or molecules are typically, constrained to not move around too much. In solids, especially if it's like an ionic solid, they're really not moving around at all. They're just kind of vibrating, right? Liquids, they're moving around each other, but still staying really close contact. Gases, all bets are off, right? Gas is totally different animal. These molecules are just whizzing by each other, very low density. They don't really interact with each other very much at all, right? And liquids and gases, of course, we have one word for those. We call fluids, right? Because they flow, right? So if we think about that, why they flow and solids don't, well, solids are feeling very strong effects of their intermolecular forces, right? The intermolecular forces matter in solids. So that means that solids have a fixed size and shape because of those strong intermolecular forces. A liquid, on the other hand, intermolecular forces are important, holds everything together, at least enough to give it a size. That is, liquids have a fixed volume. but not enough to give it a definite shape, right? And finally, gases, very minimal effects of intermolecular forces there, right? So gases have neither size nor shape. They'll just expand to fill whatever you happen to put them in. Right. So let's talk a little more about gases. We're kind of going to skip liquids because honestly, liquids are complicated, right? We have a lot of simplifications we can make about solids and a lot of simplifications we can make about gases. Any detailed study of like liquids from like a chemical physics point of view, it's really tough stuff. So anyway, we'll move right on by to gases. But first, let's talk a little bit about temperature, right? So let's imagine the gas molecules in the room you're sitting in right now. Right, they're moving around all over the place, whizzing by left, right, up, and down. But really, they're certainly not all moving at the same speed. Right, there's something called the Maxwell Boltzmann distribution, which helps us understand the speed at which those molecules are moving. Right, I'm going to draw three curves here at three different temperatures. Here in Kelvin, right, Kelvin where 0 is absolute 0. And you can see that they all have like an average speed. And clearly the average speed at 1,000 Kelvin is greater than the average speed at 300 Kelvin and is greater than the average speed at 100 Kelvin. But there's a really wide distribution here, right? Even if I look at 1,000 Kelvin gas, there's still plenty of molecules in 1,000 Kelvin gas that are moving slower than some of the molecules in 100 Kelvin gas. Right, it's just that the average is really larger, right? So when you're kind of conceptualizing these molecules moving around in a gas, we want to imagine a great variety in those speeds. Clearly, the hotter it is, the average speed is larger, because really, what is temperature? Right? If I were to give a definition of temperature, it's really the average kinetic energy of the particles that make up a substance, right? For those of you who haven't taken physics recently, kinetic energy is 1/2 mass times velocity squared. So the faster something is moving, the more kinetic energy it has, right? So really then, temperature in Kelvin is simply proportional directly to kinetic energy. Right. That is, if I have a bunch of gas over here at 500 Kelvin and a bunch over here at 1,000 Kelvin, the molecules at 1,000 Kelvin have literally twice as much energy, kinetic energy, as those at 500 Kelvin. Right. That only, of course, works in Kelvin. Right. Does not work in Fahrenheit or Celsius. Right. I mean, it's kind of a nice day out today. It's around 70 degrees. That doesn't mean it's twice as hot as a 35-degree day. Right. But if we put those in kelvins, the ratio actually would make sense. So gases, and of course, the most common model for gases that you know about is our friend, the ideal gas law. Right. So what is the ideal gas law? We're going to make a bunch of assumptions. Let's imagine we got a box of volume V. We're going to put a bunch of gas particles in there. According to the ideal gas law, however, we're going to make a couple of assumptions about those. First, we're going to say those particles are points. They have no volume. They can't hit each other because they don't have any volume. We're also going to say that they undergo continuous random motion. They're bopping around this way, that way, with speeds according to that Maxwell-Boltzmann distribution that we just talked about. Higher temperatures, higher average velocity, but quite the range. Also, those particles are sometimes going to bang off the sides of the container, right? And that's going to exert a pressure, right? And we're going to assume that those collisions are what we call perfectly elastic. That is, energy isn't lost, right? And finally, all those beautiful intermolecular forces we talked about, yep, we blow them all off for the ideal gas law. Right. So really, when it comes to ideal gas law, there's no difference between oxygen or nitrogen or helium or any gas. Right. The size is gone. The intermolecular forces are gone. They're all just points. You might be asking yourself, well, why would we do that? Well, we do that because actually, it's not a bad approximation. Right. Because what did we say was true in these gases? Are the molecules really interacting with each other a lot? No, they're not. So neglecting those few interactions turns out to be okay. And it turns out to be okay at when the gases aren't very dense, right? And that would be, as we're going to talk about in a moment, at high temperatures and low pressures. right? The temperature and pressure in the room you're in right now would kind of qualify as high temperature and low pressure, right? Atmospheric pressure is low pressure. The temperature that you're currently enjoying in your home is a relatively low temperature, chemically speaking, right? So the ideal gas law is a decent approximation, like at room temperature and pressure, which is why we care about it. Otherwise, if it didn't work, we probably wouldn't use it so darn much. So what does the ideal gas law say, right? PV equals nRT. You also see it written a lot as the combined gas law, PV over T equals PV over T. That's simply, divide the ideal gas law by T and you just got N and R, right? R is a constant of the universe, right? So if you have the same amount of gas, N and R are constant, so then P, V, and T are constant. So which one of these equations you're going to use kind of depends on whether or not you have one set of conditions or two sets of conditions, right? As soon as you see like a problem with two volumes or two temperatures, probably going to be using that combined gas law form. And also we have Dalton's laws here. So the subscripts just mean partial pressure, right? If I have a mixture of gases, like, oh, I don't know, the gas you're breathing right now, right? It's mostly nitrogen, a bunch of oxygen, a little CO2, and then trace bits of that other things, right? So the pressure in the room is partially exerted by nitrogen molecules banging against the walls and partially by oxygen molecules. So the pressure of the nitrogen, we call the partial pressure of nitrogen. And here the partial pressure really is simply the mole fraction of that species times the total pressure, right? Where the mole fraction is simply the ratio of the number of moles to the total. And there's our gas law constant of the universe. One final thing I do want to say before we move into an ideal gas law problem or two is just to understand the relationship between these quantities, right? Let's imagine we plotted pressure and volume. Right, you'll notice that those are on the same side of the equation on the ideal gas law. So it turns out that they're inversely related. As one goes up, the other goes down, right? And that's what we call inversely proportional. Looks like that graph of y equals 1 over x that you worried about back in Algebra 2 days. On the other hand, if I pick quantities that are on opposite sides of the ideal gas law, volume and temperature, or pressure and temperature, those guys are going to be directly related, right? That's going to be a straight line, right? I have seen questions based on your understanding of those things, so just good to keep in mind. Well, let's finish the day with just a quick ideal gas law calculation or two, since today's been very conceptual and we haven't gotten our hands dirty and done any math. Let's fix that. So first toy problem here. Let's calculate the density in grams per liter, because mass over volume is density, of carbon dioxide at 29 degrees Celsius and 0.92 atmospheres, which is basically, the air you're breathing out on a really hot, sticky day. So how do we do that? Well, first, let's assume 1 mole of carbon dioxide. Why? Because we didn't really have a volume. And well, if I just figure out the mass of 1 mole and the volume of 1 mole, I should be in business, right? So let's do that. PV equals nRT. So if I rearrange that real quick, V equals nRT over P. Oh, and good thing I have all those things, right? We were assuming 1 mole. The gas constant is the gas constant, right? Temperature in Kelvin, thank you very much. Never ever Celsius for the ideal gas law. So we just add our 273, right, to get to 302, divide by our pressure, 0.92 atmospheres, and out pops the volume of 1 mole of gas, right? So if you're thinking about how big is 1 mole of gas, it's about this big, right? It's like 26.9 liters in this case specifically. Well, how much does that 26.9 liters weigh? Well, that's really baby stoichiometry, right? I just find the molecular weight of CO2, which happens to be 44 grams per mole. So then that 1 mole weighs 44 grams. So the density would just be 44 grams divided by 26.9 liters, or 1.63 grams per liter, right? So as a fun exercise, right? That's a little heavy because CO2 is a little heavy, but air typically it's about 1.29 grams per liter, right? So you can do things with that number, like, I don't know, calculate the weight of all of the air in the room that you're currently in. I suggest you all do that. The answer might actually surprise you. You don't think of air as weighing much, but it kind of adds up after a while. One more problem. This one's a little fancier. So we've got a 6-liter box that's divided into 2 compartments, one 4-liter and filled with filled with oxygen at a pressure of 2 atmospheres, and then a smaller compartment that's 2 liters filled with nitrogen at a pressure of 1.5 atmospheres. You might see what's going to happen here. I'm going to release the divider, allow these gases to mix, and I'm asking you what's going to be the total pressure in the box, and really the partial pressures of each species after they're allowed to mix. Right. So here, we're not going to use the straight up form of the ideal gas law. We're going to use the combined gas law. Why? Because we have two properties, right? We have an initial volume and a final volume. Temperature here, not changing at all, so we can kind of blow that part off, right? Also, we remember that they're ideal gases. They don't even know the others there. So I can do this problem in two parts. I can just imagine, okay, let me think about the nitrogen, or let me think about the oxygen. I'm going to start first with the oxygen. Great. So our combined gas law now simply says PV equals PV because the temperature is the same, so that just went away. If I rearrange that a little bit, P2 is just equal to P1 V1 over V2. Oh, good. I know those things, right? For oxygen, the initial pressure was 2 atmospheres. The initial volume was 4 liters. And once I release the divider, the new total volume is going to be 6 liters. So that same amount of oxygen in the larger container will only be at a pressure of 1.33 atmospheres. So that really is the partial pressure of oxygen once they mix. Because again, they're mixing, but they're not really interacting because they're ideal gases, and ideal gases don't do that. Moving on to nitrogen, same deal, right? So just skipping a step or two, getting to our P2 equals, in this case, 1.5 was the initial pressure, 2 was the initial volume, divided by our same final volume, because same box, and we find that the final pressure of nitrogen is only 1/2 atmosphere. So therefore, the very final pressure in the box is 1.83 atmospheres because I simply add those up. Thank you, Dalton's law of partial pressures. I think that takes me to about the end. It's, I think, about the right time. So appreciate your joining me today. I hope it was fun for you. Next week, we're going to do more quote unquote chemistry in our chemistry. The big idea is called transformations, but really it's all about chemical reactions. So next week's going to be a whirlwind of different types of chemical reactions and kinetics and a little bit of thermodynamics and equilibrium. I am sure you will not want to miss it. So I look forward to seeing all of you again next week, same time, same channel. I'll see you then.